talking about limits algebraically, we're no longer going to be looking at the graph like in section 3.1. Now we're actually going to be looking at the algebra behind evaluating limits. Sometimes these will be easy. As with the graphs, we can just look, substitute in, and do a bit of calculating. Sometimes they will be a little bit more difficult to deal with. We might have to manipulate, do some factoring, or perhaps some other things. So the first basic method is direct substitution. This is a method that we actually always do no matter which strategy we're using for evaluating limits. We just don't always use it explicitly. Sometimes we'll use it as a step 1 to see what step 2 has to be. Sometimes it is the end. So to deal with direct substitution, we literally take the value that the limit approaches, in this case x equals -3, and substitute that in to the limit. Working out the math, we get 6 over -6, which would be -1. In B, same thing, we substitute in the 2, so we get 2 cubed minus 3 times 2 squared. 2 cubed is 8, minus 3 times that's 4, so 8 minus 12, so -4. Easy enough when direct substitution works. And by works, I mean we get a unique answer. When direct substitution doesn't work, we end up getting an undefined or an indeterminate form. So 0 on the bottom of a fraction. We don't want that. So 0 on the bottom either leaves us with the undefined infinity, indeterminate 0 over 0. We cannot use direct substitution as the be-all, end-all if this is the situation we have. If we get that situation, we have a couple of options to deal with, and the difficulty lies in deciding which of those options to use. The most common one will be factoring. So we take a look at the top and the bottom, see what's factorable, and go from there. So why do we have to use factoring on this? Well, if we take a look and we were to direct substitute 5 in for x on the bottom, we would have 5 minus 5, which is 0. It doesn't matter what the top is, if it's 0 or if it's something else. This will give us either undefined or indeterminate, and that is not okay. So what we need to do is look to factor this, and as I'm doing this, you're going to notice now I'm actually writing limit x approaches 5 in the next step. That has to stay here until we substitute a number in. We will eventually go back to direct substitution. We just can't do it yet with the way that this is set up. Looking at the top, x squared minus 6x plus 5, do we have two numbers that would multiply to 5 and add to -6? Yes, we do. That would be x minus 5 and x minus 1. On the bottom, that's not factorable, so we'll just leave it as x minus 5, but we should be able to see at this point what we're able to do because of the factoring on top is we can cancel the x minus 5s, and we're left with the limit as x approaches 5 of x minus 1. Now here we can go back to direct substitution, substitute that 5 in directly, calculate out, the answer is 4. So direct substitution at the beginning to see if it will work. If it does, go ahead and do it. If it doesn't, we need to come up with a method to make it work. Factoring was the one that worked here. We might also have a more complicated top or a complicated bottom. Factoring might not be possible. We can look to simplify, and really what it means is expanding brackets. FOIL multiplication is going to come into play in a situation like this. We still need to check direct substitution. We need to take a 0, substitute in for the h, and we see that the bottom does turn into 0, so direct substitution is not going to work completely. What we do need to do is actually multiply this out and see what we can do. I'm only going to do one thing off the top. I'm literally going to get rid of that exponent of 2 and leave that as negative 2 plus h, negative 2 plus h. I'm not going to touch anything else because it's not going to save me any steps, and it's really not going to save me any writing either. So again, I'm putting limit h approaches 0 on every step until I substitute in for my final answer. I need to FOIL out these brackets here. So start off with negative 2 times negative 2. That is 4. Negative 2 times h minus 2h. Going inside, h times negative 2, another negative 2h. And the last one's h times h plus h squared. Continuing on, this minus 2 needs to get distributed into that bracket, so negative 2 times negative 2 would be plus 4. And again, negative 2 times h would be minus 2h. And we have the minus 8. That's going to carry on at the end. And we're all over h. Taking a look, by expanding this out, we've actually created the potentiality for some like terms. I like going exponents highest to lowest, so I'm going to deal with it that way. We have h squared, nothing like with it, so it can just be there. We have minus 2h, minus 2h, minus 2h. Combining those gives us minus 6h. And we have 4 plus 4 minus 8, which works out to 0. And this is still over h. Looking at this now, we've expanded, we've simplified, we've combined like terms. I wonder if I substitute in 0 for h, nope, I'm still going to get a 0 on the bottom. So there needs to be something else I can do to this, and if we're looking at the top, there is a common factor of h that can come out. That is going to be a very common thing to do, especially when we get the situation of a limit as h approaches 0. So if we take that h out on top, we get h minus 6 left over, and that is still over h. But what that allows us to do is to now cancel these h's. Leads us to the limit as h approaches 0, now of h minus 6. Now we can actually substitute that 0 in for h, not get a 0 on the bottom because we've eliminated that. And now is the step where I can stop writing that limit because now I've substituted in the number, do the math, and after all that we get an answer of negative 6. So expanding does take a long time. It does get a little bit ugly, but it does condense itself down quite nicely at the end. The last method we will talk about in Calculus 30 is rationalizing. This method applies only if we have radicals present, roots. They may be in the numerator, they may be in the denominator, it doesn't matter, but there is a process to rationalize if we have a root and if we need to. So looking at this limit, we have the limit as x approaches 100. Let's see, direct substitute 100 into there. We get a 0 on the bottom, which is no good, so we will need to rationalize. That involves multiplying by something called the conjugate of the root. So the root here is root x minus 10. We need to multiply by the conjugate of it. And a conjugate is just the same terms, but with the opposite sign in between them. And if we do that on the top, we also need to do that on the bottom. The process here, we are going to FOIL out the top. We are not going to FOIL out the bottom. I will explain why we don't FOIL the bottom once we get to the point where it will make sense. But doing the top, root x times root x is just x. Root x times 10 is plus 10 root x. The 10 is outside a root, the x is inside. They can't multiply together, they are not like. The inside bits, we have negative 10 times root x, which is minus 10 root x. And the last bits, we have 10 times 10, sorry, negative 10 times 10, which is minus 100. That is over, and I said I'm not going to FOIL out the bottom for reasons which I will make clear in the next step. We are just going to write it as is. In the next step, we will have like terms where we multiply by the conjugate. That is the purpose of multiplying by the conjugate. Specifically, those two right there, they by design will cancel each other out. That's the whole point of picking the conjugate. What that leaves us with on top is just x minus 100. The bottom is what it just was, and at this point, it should hopefully be clear why I didn't FOIL out the bottom. Because the design of picking the conjugate the way we do not only gets rid of the roots, it also creates a place where we can cancel. Now, do not forget, this is still a fraction. When we cancel, things cancel to a 1. So this is 1 over the square root of x plus 10. And I need to apologize. I have been putting limit h approaches 0 on every single one of these. This should actually be limit x approaches 100. Picky little detail up until now, but at this point it becomes extremely important because that's now the number that we plug in for x in the limit. So this now becomes 1 over square root of 100 plus 10. Taking the square root of 100, that's 10, still plus 10, and working that out, 1 over 20. So choosing which method to deal with in order to simplify the limit before going back to direct substitution is the biggest challenge to this. If you see a root in the limit, rationalizing is going to be what you have to do. If you see a bracket with an exponent on it, you will have to expand and multiply out. If you see none of that, factoring is likely the only option. In most cases, it's actually the quickest and probably the easiest way, but just know that the other ways are there and what to look for when we see those.